Ready to dive into the world of movie magic and video game visuals.
Oh, yeah.
Today, we're exploring physically based shading, that tech wizardry that makes digital worlds look unbelievably real. We've got a stack of presentations from SIGGRAPH 2020, straight from the minds of industry giants.
Yeah, it's incredible to see how far we've come. We've gone from artists basically hand painting light onto objects to this incredibly sophisticated approach that's all about simulating how light actually behaves.
It's like the difference between drawing a smiley face sun and recreating the blinding glare off a glacier, right?
Whoa.
We're talking about light bouncing around a scene, interacting with different materials in a way that just feels real.
And what's fascinating is how the shift to physically based shading, or PBS, didn't just make things prettier. It fundamentally changed the way developers approach creating these digital worlds.
Okay, let's unpack that a bit. What do you mean?
Well, think about it. Before PBS, artists were stuck with these handcrafted shaders, spending hours tweaking individual parameters to get the look they wanted. It was inefficient, inconsistent, and let's be honest, probably drove a lot of artists crazy.
I can only imagine the frustration of trying to make a forest look realistic when every leaf seems to have a mind of its own.
Exactly. But with PBS, there's this emphasis on working within the rules of physics. We're talking about energy conservation, accurate light properties, actually thinking about how light behaves in the real world and applying those principles to the digital one.
So it's less about artistic guesswork and more about understanding the science behind how light interacts with the world.
Precisely. And this shift is really evident when you look at the move from multipass rendering to single-pass path tracing, especially in the film world.
Ooh, now those are some fancy terms.
Yeah.
Can you break it down for us?
Sure. In the past, to get those photorealistic effects, studios like MPC, the masterminds behind movies like The Jungle Book, were using all these different rendering techniques like shadow maps and point clouds. Imagine layering multiple filters onto a photograph to achieve a certain look. Each technique added another layer of complexity to the process.
I'm getting a headache just thinking about managing all those layers of data. It's like trying to bake a cake while juggling a dozen eggs.
But it was a highly complex process, but then along came the RAS framework in RenderMan, a powerful rendering software. This allowed studios like MPC to transition to a single-pass path tracing method. Instead of rendering different elements separately, they could now simulate the entire path of light rays as they bounced around a scene.
So less juggling, more like watching those light rays dance across a ballroom.
Exactly. It's a much more elegant and efficient way to achieve realism. And this shift to PBS and single-pass path tracing opened the door for new techniques and challenges, especially when it comes to rendering specific materials realistically.
Like fur, for example.
Yeah.
I remember watching The Lion King and being amazed by how real the fur looked. You could practically feel the texture.
Absolutely. Achieving that level of detail for something like fur or even skin is a whole other deep dive in and of itself. But before we get there, let's talk about a fundamental concept that's crucial for understanding PBS, the Fresnel effect.
Hit me with it.
You know, when you look at a window straight on, you can see right through it. But
Yeah.
if you look at it from an angle, it becomes more reflective.
Yeah, like my phone screen. Impossible to read head-on in the sunlight. Perfect mirror from the side.
Exactly. That's the Fresnel effect. And accurately simulating it is essential for realistic shading.
So how do they do it? Is there like a Fresnel equation or something?
There is, but it can be quite computationally expensive. A clever solution highlighted by Nady Hoffman in one of our SIGGRAPH presentations is the Schlick approximation. It's a simpler and faster way to achieve a similar result.
A trade-off for the sake of efficiency, then.
Precisely. The Schlick approximation might not be perfectly accurate in every scenario, but it's often more than enough for most use cases, especially in real-time rendering where speed is crucial. What's remarkable is that this approximation, initially designed for surfaces like glass and plastic, can also be adapted for external media.
External media, meaning.
Rendering things underwater, for example.
Hmm.
Even though light behaves differently in water, the Schlick approximation can still be tweaked to get surprisingly accurate results. It's a testament to its versatility.
That's impressive. So we've got light bouncing around realistically. We've tackled the Fresnel effect.
Mm-hmm.
What other tools are in these developers' arsenal?
Well, let's talk about anisotropy next. Have you ever noticed how brushed metal has this sort of directional sheen to it?
Yeah, like the back of my laptop. The way it catches the light changes depending on how I tilt it.
Exactly. That's anisotropy. And rendering it accurately, especially in a visually stunning game like Ghost of Tsushima, is no easy feat.
I'm guessing the developers at Sucker Punch, the studio behind Ghost of Tsushima, had to get creative to achieve that level of detail.
They did. Let's dive into their approach to anisotropic reflections right after this quick break.
All right, so we were about to hear how the wizards at Sucker Punch tackled anisotropic reflections in Ghost of Tsushima. It's amazing how those details can really bring a world to life.
Oh, absolutely. It's all about those subtle cues that make a surface feel real. In their presentations, Sucker Punch talks about their innovative SGGX-based filtering technique. They were previously using something called lean filtering, but it had limitations, especially with strongly anisotropic materials. Their new method delivered those beautiful, shifting highlights you see on things like brushed metal in the game.
And I'm guessing they were mindful of performance, especially given the scale and visual fidelity of Ghost of Tsushima.
Absolutely. They actually came up with a new way to encode anisotropic roughness textures that use significantly less memory than the Lannan encoding. It's a fantastic example of developers finding that sweet spot between stunning visuals and smooth performance.
Speaking of stunning visuals, we can't forget about that incredibly realistic fur in The Lion King. I'm dying to know how MPC pulled that off.
Get ready for some serious fur physics. MPC wanted to go beyond simply making fur look good. They wanted to make it behave realistically, capturing how light interacts with individual hairs.
Because a lion's mane isn't just a static texture, right? It's this dynamic, flowing element that catches the light in different ways.
Exactly. So they started with the double-cylinder model, which focuses on simulating the medulla, the core of a hair.
Wow, they were really thinking about this at a microscopic level.
It's all about the details. The way light scatters within the medulla is crucial to how we perceive the color and texture of fur. MPC even developed a modified Henny-Greenstein phase function to approximate this scattering accurately.
Hold on, you lost me at function. Can you break that down a bit?
Sure, think of it as a mathematical formula that describes how light is scattered in different directions. By tweaking this formula, they could control how light interacted with the fur, giving it that realistic, almost luminous quality.
So it's not just about the shape of the hair, but how light bounces around inside it.
You got it. And the number of bounces has a huge impact on the final look. For The Lion King, they used a whopping 8 to 10 bounces per hair, which contributed to that rich, vibrant look.
8 to 10 bounces. That's like a pinball machine of light inside each hair. No wonder it looks so good. But I'm guessing all those bounces are computationally expensive.
You're right, but they had a trick up their sleeves. They used a technique called multiple importance sampling to keep things running smoothly. This method strategically focuses the rendering effort where it matters most, ensuring efficient use of processing power.
Smart. So they're thinking about both the artistry and the technical execution.
Exactly. It's a delicate balance. And speaking of balance, rendering realistic skin presents its own set of challenges. We've all seen games or movies where the skin looks plastic or lifeless.
So that uncanny valley effect, right? Something
Yeah.
feels slightly off.
Right. Skin has this translucent quality, this subtle scattering of light beneath the surface that's incredibly difficult to replicate. But the developers at Sucker Punch, with their work on Ghost of Tsushima, took on that challenge head-on.
Okay, I'm all ears. What did they do?
They went beyond the standard subsurface scattering techniques and introduced something called curvature-based diffuse shading. This technique adds incredibly fine details and shadowing to the skin, giving it a much more realistic and nuanced look.
So it's like they're sculpting the skin at a microscopic level, just with light and code.
That's a great way to put it. They experimented with different types of curvature, like mean curvature and directional curvature, to see how they impacted the final look.
It's amazing how these tiny details can have such a big impact on realism. But with all these complex materials and techniques, how do developers keep things organized and ensure that assets can be easily shared and used across different platforms and software?
That's where the world of material description languages comes into play. Remember Material X, that universal language for describing materials we talked about earlier? It's like the Rosetta Stone for computer graphics.
It sounds like an essential tool for collaboration and streamlining the creative process.
Absolutely. And there are other players in this field as well. Have you heard of MDL, or Material Definition Language?
That rings a bell. Is that similar to Material X?
It is, in the sense that it provides a standardized way to describe materials. But MDL has gained a lot of traction in the world of offline rendering, which has its own unique set of demands and possibilities.
Okay, I'm intrigued. Tell me more about this offline rendering and where MDL fits into the picture.
So offline rendering is that, like the director's cut of the CGI world, where you have more time to perfect every detail?
You could say that. Offline rendering is all about pushing visual fidelity to the max. It's what's used for films, high-end animation, those incredibly detailed CGI shots that leave you wondering if it's real or computer-generated.
So we're talking about the kind of detail that would bring a gaming PC to its knees if you tried to render it in real time.
Exactly. Because
Okay.
you're not constrained by the need to render everything on the fly, offline rendering allows for much more complex calculations and simulations, and that's where MDL really shines.
So how does MDL differ from Material X in the context of offline rendering? Well, think of it this way. Material X is like a universal translator, ensuring that different software and rendering engines can understand how a material should look. MDL, on the other hand, is more like a master craftsman's toolbox, allowing for incredible precision and control over the nuances of a material's appearance.
So Material X is about accessibility, while MDL is about pushing the boundaries of what's visually possible.
That's a great way to put it. We're seeing software like V-Ray fully embracing MDL, and even RenderMan, the industry standard rendering software, is exploring ways to incorporate it.
It sounds like MDL is gaining a lot of traction. Is this blurring the lines between real-time and offline rendering?
It's definitely pushing the boundaries. As hardware and software continue to advance, techniques that were once exclusive to offline rendering are starting to find their way into the real-time world. It's an exciting time to be following the evolution of these technologies.
It really is remarkable to see how quickly things are progressing. But even with all these advancements, I imagine there are still times when you need to step outside the lines of pure physics to achieve a specific artistic vision.
Absolutely. There are moments when a director might say, I need that reflection to hit at just this angle to emphasize the character's emotion, or let's tweak that shadow to create a sense of foreboding. Artistic expression still reigns supreme.
So it's like having this incredibly precise, scientifically accurate toolkit, but knowing when to use it intuitively as well.
Precisely. And this interplay between technology and artistic vision is even extending into non-photorealistic rendering, where the goal is to emulate different artistic styles.
That's fascinating. So instead of trying to create a perfect simulation of reality, you're using these tools to mimic, say, the look of a watercolor painting or a charcoal drawing.
Exactly. And we're seeing some truly groundbreaking work in this area. MPC, for instance, is experimenting with incredibly detailed lens simulations, going beyond simple models to capture the unique imperfections and characteristics of real-world camera lenses.
It's like giving digital artists the ability to choose their lenses like a photographer would, but with even greater control and flexibility.
And this raises some interesting questions. How much control should artists have over these simulations? Do you provide the parameters of a real lens or allow for customization, even the creation of entirely new virtual lenses?
It's that constant push and pull between realism and artistic license. Fascinating.
And as these tools evolve, we'll likely see even more of that, with artists pushing boundaries and exploring uncharted visual territories. The future of physically based shading is incredibly exciting, and I, for one, can't wait to see what visual wonders await us.
Well said. It's been quite a journey exploring the world of physically based shading, from its origins in the pursuit of realism to its potential for pushing artistic boundaries. We've covered a lot of ground today, but as with any good deep dive, it's only sparked more questions and the thirst for further exploration. Until next time, keep those creative gears turning.